Welcome to the Crazy Hat Chemist. So today we're doing another video in bonding and molecular structure. So let's get moving. Bam! This is a big one. Molecular geometry. We are following the ax. Remember the A for the ax is the central element. Then the X for the ax is the surrounding elements. The E are the lone pairs of electrons on the central element. I want you to take a look at what you have on the yellow at the very top. To the left, starting with the left, is the shape name, then the axe-like structure, AXE, the generic shape, the hybridization, the 3D ball and stick molecular shape, and the bond angles, and then following that is the bonding and non-bonding finally. We're going to go through all the molecular geometry of all the shapes. So let's get started with the first one. The first one is a linear shape. It's AX2. You should see with that generic Lewis dot structure. You have the A, the central element in the middle, the two X's on the outside. The hybridization is SP. The 3D ball and stick model is linear in shape. Its bond angles of 180 degrees, and you have 2 bonding and 0 non-bonding. I'm going to show that to you. Here it is, right here. So here it is. The A is in the middle. I'm holding on to that. The X are on the outside, and these gray areas are the bonding pairs of electrons here. Okay, so for hybridization, you should see that it's sp hybridized. There are two domains around the central element. These atoms are linear to each other. Hopefully that makes sense. That's why the bond angle is 180. And there's A, X1, X2, SP1 hybridized. Okay, that's linear. Let's do the next one. Here's the next one right here. That is trigonal planar. So trigonal planar is AX3. You should see the generic Lewis dot structure with that A in the middle and 3 bonding pairs around it. It's SP2 hybridized. The ball and stick model is like that you see there. The bond angles are 120, and there are 3 bonding and 0 non-bonding pairs. I'm going to show you that here with this ball and stick model here, if you will. Same kind of thing here. This is a trigonal planar structure. Notice that all the atoms are in the same plane. That is, the outside atoms and the central atom are in the same plane. If you think about a circle being 360 degrees, then divide that by 3 because you have 3 bonding domains around it. Divide that by 3, you get 120. So each of these bond angles here is 120 degrees. Okay? Trigonal planar. Lovely structure. Now what we're going to do is we're going to take away one of the bonding pairs and replace it with a lone pair of electrons, and then we are going to get this structure, which is a bent or angular structure. It's AX2E, and I want to point out that Lewis dot structure, that A in the middle with the lone pair of electrons, that is the E. That's where that E is coming from. So hopefully you see that. And there are 2 bonding domains. That's the 2 X's. It is SP2 hybridized. There's the ball and stick model. The bond angles are less than 120, and the bonding and non-bonding domains around the central element are 2 and 1 respectively. I'm going to show you that like structure right here. I'm holding on to the lone pair of electrons here. This is the central element, and the green ones here are the bonding pairs. Okay. Now you should see that this lone pair that I'm holding on to right here, okay, is compressing this bond angle. You would think that it would be 120, okay, but it's compressing the bond angle because these lone pairs are delocalized electrons, and they push that away. These are localized electrons. That is, they are localized in between the central element and the outside element. Those are localized. These are delocalized. They have nothing to bond onto. That's why there's a compression of bond angles due to lone pairs of electrons. So you should see that this is SP1, P2 hybridized. Okay. One more thing about anything that is bent or angular, okay, it is polar in structure no matter what, because this is an asymmetrical shape. That is, this side is different than this side. That makes it asymmetrical and therefore polar no matter what. Okay, all right, so let's get moving on to the next set here. The next set is right here. The first one of this next set is tetrahedral. It is AX4. The generic Lewis dot structure is the A in the middle. You got 4 bonding domains of the 4 X's. It is SP3 hybridized. There's that ball and stick model. The bond angles are 109.5, and there are 4 bonding and 0 non-bonding. I'm going to show that to you here, right here. And this is the tetrahedral structure right here. Tetrahedral structure. That means that this bond angle right here is 109.5. This bond angle is 109.5. This is following Vesper geometry, which means that you're reducing the electron pair repulsions. That means that these atoms need to be as far away as possible three-dimensionally, and that gets you the corners of a tetrahedron right here. That's why this is tetrahedral in structure. As far as the hybridization, watch carefully. This is S, P1, P2, P3 hybridized. Okay, hopefully that makes sense for you. Let's keep on moving. Now what we're going to do is we're going to rip off a pair of bonding pair, we're going to replace it with a lone pair of electrons, and then we get our next structure, and that is Trigonal Pyramidal. That is AX3E. There's a lone pair of electrons on that A in the center, and then you've got three bonding domains. That's sp3 hybridized, the same hybridization as a tetrahedral. There's that ball and stick model with that 3D shape. The bond angles are less than 109.5, and it's 3 and 1 for the bonding and non-bonding respectively. So check that out. This is that structure right here. This is the lone pair of electrons that I'm holding onto right now, and then the three bonding pairs are right here, and then the central element in the blue right there. Now this one in particular is ammonia, okay? And you should see, just like with the bent-like structure that we discussed before, this lone pair of electrons is delocalized, and it's compressing the bond angles of all the other bonding pairs. It's a tetrahedral arrangement of electron domains. However, it's a compression of bond angles due to this lone pair of electrons that I'm holding onto. That's why it's less than 109.5. Okay? And the question is, if I rip off a lone pair, if I rip off a bonding pair, and then from that, what do I get? I get the next structure, and that is Benter angular. Benter angular is, this is the second Benter angular, but this Benter angular has two sets of lone pairs of electrons on it and two bonding pairs, instead of one set of lone pairs of electrons. The axe-like shape is AX2E2, okay? You should see the Lewis dot structure generically there. It's sp3 hybridized. There's that ball and stick model. It's much less than 109.5, and it's 2 and 2 as far as bonding and non-bonding respectively. I'm going to show that to you right here. It almost looks like a Mickey Mouse-like structure right here. These are the two bondings. These are the two non-bondings. That red in the middle is the central element. Okay, now the lone pairs of electrons right here, these are the lone pairs of electrons, they are going to compress this bond angle. That's why this bond angle is not 109.5, and it's not less than 109.5, it's even less than 109.5. Okay, some of these structures you should see are non-polar based on their shape, and that is Trigonal Pyramidal is polar based on its shape, and same with angular or bent. That is, this side is most certainly different than this side. That makes it polar. Not that you shave it right down in the middle here, okay? It doesn't matter. This side is different than this side. That makes this polar, okay? And then I want you to make sure that you understand that this one here is also polar here, and it is Trigonal Pyramidal, and it's not Trigonal Planar. Notice that the blue and the white are not in the same plane. That's why it's not Trigonal Planar. It's Trigonal Pyramidal. Okay? All right, so now I'm going to show you the bond angles for ammonia specifically, 107, and for water specifically at 105. All of these are sp3 hybridized, and it's really the lone pairs of electrons on the central element that are compressing that bond angle, and you should see that compression of bond angle right there. That's a beautiful thing. Okay, let's go to the next set. The next set is right here, is Trigonal Bipyramidal. Trigonal Bipyramidal is AX5. You should see that the A is in the center, and then you got 5 bonding domains. Obviously, this one is exceeding the octet rule, and everything that we talk about from here on out is exceeding the octet rule. It is sp3 dehybridized, that ball and stick model in the 3D shape is right there. The bond angles are a set of bond angles. Of one of the sets is 90, the other one is 120, and there are 5 bonding and 0 non-bonding domains. I'm going to show you this structure right here. Okay, you should see that it's trigonal planar, and of course these bond angles, as we already discussed with the trigonal planar structure, are 120, and then at the poles this is 90, just like it looks. So it's Trigonal Bipyramidal. So there's the base of my pyramid in that trigonal planar structure, and there's a pyramid here and a pyramid here. That's why it's bipyramidal, because there's 2 pyramids, one on top, one below. Okay, and then the bond angles 120 and 90. Hopefully that one makes sense here. Trigonal Bipyramidal in shape. This is one of my favorite ones. I love this one. Trigonal Bipyramidal. Okay, all right, let's go to the next one. Now, I want you to think about this question. I'm going to put a lone pair of electrons on this, but I need as much space as possible for that lone pair of electrons. So is it going to go at the poles that I'm touching here, or is it going to go in the trigonal planar structure? Well, lone pairs require as much space as possible. So where is the most amount of space? It's in the 120. So it's going to go inside this central region right here, because that's 120 as opposed to the 90. Okay, so that is our next structure. Our next structure is disphonoidal or seesaw, and that's AX4E. There's that basic Lewis dot structure. It is also sp3 dehybridized, and there's that ball and stick model. It's less than 90 and less than 120. There's 4 bonding, 1 non-bonding domain. And I'm going to show you that structure right here. You should see that this is the structure, and this is the seesaw shape. You should also see that that lone pair of electrons is within that planar structure because it requires more space. That's why it's in the 120-degree space. This lone pair of electrons is compressing all the bonding pairs. That's why it's less than 90, less than 120, and you get the 4 and 1. Okay, I want you to think about the polarity of this one here. Is it asymmetric or symmetrical? Think about that. This side is different than this side. This top end is different than the bottom end. That's asymmetrical. That's most certainly polar. I'm going to pop that up a little bit later on. This is one of my favorite shapes, disphonoidal or seesaw. There's the seesaw. All right, there's the seesaw, disphonoidal seesaw. Now we're going to rip off a pair of bonding pairs, again in the central region here, because that's where as much space as possible. And then what we're going to do is we're going to put a lone pair of electrons on that, and that's going to give us our T-shape. Our T-shape is AX3E2. There's the basic Lewis dot structure there. It is also sp3 dehybridized, a ball and stick model. It's less than 90 degrees. It's 3 and 2 with bonding and non-bonding respectively. I'll show you that right here. Here is that structure. You should see that this is T-shaped. T-shaped, 2 lone pairs of electrons on the central region within the trigonal planar structure. Okay, and these lone pairs of electrons here are going to compress these bond angles. That's why it's less than 90 degrees. Think about this. Is this asymmetrical or symmetrical? This is most certainly this side is different than this side. It doesn't matter how you turn it. This side is different than this side. That is going to be asymmetrical, and that deals with the polarity. Okay, I pity the fool. I'm Mr. T. Check it out. All right, let's go with the next one. The next one is going to be taking up this bonding pair, put a lone pair on that central region within that same amount of region there, and that is a linear-like structure. That's AX2E3. There's a basic Lewis dot structure. It is sp3 dehybridized. You should see that linear structure. It's 180 degrees. Of course it's linear. It's 2 and 3 for bonding and non-bonding, and I'm going to show you that right here. This is the linear structure. You should see that the green and the purple are linear to each other, and the tan-colored things are the lone pairs of electrons on the central region. Is this asymmetrical or symmetrical? This is most certainly symmetrical. Okay, so now I'm going to show you the polarities of the ones, and we already discussed those. And these 2 in the middle, disphonoidal, seesaw, and T-shaped, are polar. The other ones still could be polar, depending on the outside elements. But most certainly, no matter what, based on the shape, disphonoidal, seesaw, and T-shape are polar. All right, let's do our last set here. Our last set is octahedral. Okay, octahedral is AX6. There's a basic Lewis dot structure. It is sp3d2 hybridized. There's that 3D ball and stick shape. All the bond angles are 90, and there's 6 bonding and 0 non-bonding. Think about octa. Octa is for 8. So you're going to think, why is it octa for 8 and you have an AX6? So I want you to look at this structure first, and I'm going to answer that question here. You should see that this is a really cool shape. It's octahedral. That means octahedral is the faces of this 3-dimensional shape. 1, 2, 3, 4 faces of this on the top, and then there are 1, 2, 3, 4 faces on the bottom. That's why it's octahedral. All the bond angles are 90. Now what I'm going to do is I'm going to take off a pair of the bonding pair. I'm going to put a lone pair on that central region. I'm going to get my next shape. Here's my next shape. My next shape is square pyramidal. It's AX5E. You should see that basic Lewis dot structure. It is also sp3d2 hybridized. There's the ball and stick model. It's less than 90 degrees, and it's a 5 and 1 for the bonding, non-bonding. I'm going to show you that one here. I'm holding on to the lone pair of electrons right here, square pyramidal. Okay, is this asymmetrical? Most certainly. This side is different than this side. That tells you that this is most certainly polar. I'm hoping that you see the square, and then the pyramid shape. That's why it's square pyramidal. Okay, hopefully that works out well for you. This is asymmetrical. You should see that the bond angles are compressed. That's why they're less than 90. Okay, I'm going to do the hybridization on this one. I haven't done it on all of them, but it's S, P1, P2, P3, D1, D2 hybridized. All you're doing is counting the domains around the central region. Now I'm going to take a lone pair of electrons and put a lone pair of electrons on this, but removing a bonding pair, and that goes with our next shape. Our next shape is square planar. It is AX4E2, and you should see that square planar structure. It is SP3D2 hybridized. There's that ball and stick model, and I got a siren over there. Sorry about that. And we got 90 degrees, 4 and 2 bonding and non-bonding. It is square planar. There's our square planar structure. There's our square, and they are all within the same plane. Is this asymmetrical or symmetrical? This is most certainly symmetrical. Hopefully that works out well for you. Now, which one is polar out of this entire group? That is the only one that is polar out of this entire group. Okay, now I'm going to do one more thing here, so hang on because this is a good one. And I got a super cool hat at the end, so wait for the hat. Okay, so now I'm going to tell you how to memorize these shapes with their names. Okay, you're going to eat a BLTS. What is a BLTS? A BLTS is a bacon, lettuce, and tomato sandwich. Yum, got to get one of those. So, bonding pairs and lone pairs, that's what we're talking about. Okay, there's our BLTS. We're going to draw lines in between these. Now, I'm going to do one more thing here. I'm going to do the ones with no lone pairs on it. 0 and 2 is linear. Okay, so 0 and 2. So that's 2 and 0. That's linear, right? 3 and 0 is trigonal planar. Trigonal because 3. 4 and 0 is tetrahedral. Tetra for 4. That's why it's a 4 and 0. And trigonal bipyramidal. Trigonal is for 3. Bi is for 2. Add up the 3 and the 2, you get the 5. There's the 0. Okay, and then octahedral, remember there's 6 apexes. There are 8 sides, but 6 apexes. That's where you get the 6 and 0. Okay, now we got lone pairs on these sets. That's 2 and 1 lone pairs, that's bent. 2 and 2 lone pairs, that's also bent. So both of them are bent with the 2s. Okay, now we got 2 and 3, and that is linear. That's that trigonal bipyramidal structure in general. Then we got 3 and 1, that's trigonal pyramidal. We got 3 and 2, that's T-shape. Now this is in alphabetical order if you look at this. T, P, T, S. I've highlighted those in yellow there for you. Okay, 4 and 1 is seesaw or disphonoidal. 4 and 2 is square planar. We're doing this also in order of alphabetical here. And 5 and 1 is square pyramidal. So S just for seesaw, then SL for square planar, and then square pyramidal, that's S and Y. That's also in alphabetical order. Okay, I want you to know these. You have to memorize the names of the shapes with either the axe-like structure or the bonding pairs and lone pairs on the central domain. Okay, those are the domains around the central region. Okay, this is an awesome video. There's so much on this one. You got to rewind this and play it again. Play it again, Sam. Okay, so that is... I am the Crazy Hat Chemist, and I got one of my favorite hats on here from one of my former students. Thank you very much, Jacob. I really appreciate it. I hope you have a fantastic day. Give me a thumbs up if you like this video. Subscribe to my YouTube channel. Pass on my YouTube channel to all your favorite friends of chemistry, because this is the place where all the details are. The best place to learn your chemistry online is right here at the Crazy Hat Chemist. I will see you next time. Talk to you later. Bye now.